Could there be a second universe hidden inside our own? Not somewhere beyond the most distant galaxies, but concealed within the very structure of the reality surrounding us? At first, the question may sound like science fiction, yet modern physics has taught us that appearances can be deeply misleading. A region that seems small from the outside may contain an enormous interior. Two forms of matter may occupy the same space while barely noticing one another. And a boundary that looks like an ending may, from another perspective, become the beginning of an entirely new cosmos. Before we explore these possibilities, tell me quietly, what time is it where you are? And where in the world are you listening from tonight? To approach this mystery gently, we first need to understand what scientists mean when they use the word universe. In everyday speech, the universe usually means everything that exists, all matter, energy, space, time, and every law governing them. But in cosmology, the word can also be used more narrowly. It may refer to the region of reality connected to us through a shared history. A region whose light or gravitational influence could, at least in principle, reach us. This distinction matters because reality might extend beyond what we can observe. There could be domains separated from us by distance, cosmic expansion, horizon, or physical barriers so complete that no ordinary signal could cross between them. The observable universe is not necessarily the entire universe. It is simply the portion from which light has had enough time to reach us since the early stages of cosmic history. Because the universe has a finite age and light travels at a finite speed, our view is limited. We see a vast sphere centered on our present location, filled with galaxies stretching across tens of billions of light years in every direction. Yet the edge of this visible sphere is not a wall. There is no reason to think space suddenly ends there. It is better imagined as a horizon beyond which information has not reached us, like distant land hidden below the curvature of an ocean. This already gives us one simple meaning of a hidden universe. There may be regions beyond our cosmic horizon that are physically continuous with our own space but forever inaccessible to observation. They would not necessarily contain different laws, strange dimension, or exotic forms of matter. They might simply be more universe, more galaxies, more empty space, and perhaps more worlds than we could ever count. But the idea suggested by our central question is stranger. Could a distinct universe exist, not merely beyond our view, but somehow inside the region we already inhabit? Could it be nested within ours, overlapping it, or enclosed behind a boundary that disguises its true size? To see how such a possibility might arise, consider a familiar object, a sheet of paper. Imagine a tiny insect walking across its surface. To the insect, the paper may appear to be an entire two-dimensional world. It can move forward, backward, left, and right, but it cannot naturally leave the surface. Now fold the paper so that two distant points touch. From our three-dimensional viewpoint, the separation disappears. Although the insect's world still regards the points as far apart, this simple image shows how geometry can conceal relationships. A space may appear one way to creatures living inside it, and another way to an observer who can see a larger structure. Our universe is not literally a sheet folded in ordinary space, but the comparison helps us loosen our intuition. General relativity, Einstein's theory of gravity, describes space and time as a flexible geometry. Matter and energy influence this geometry, and the geometry guides the motion of matter and light. Space can expand, curve, stretch, and form horizon. Time itself can pass at different rates depending on gravity and motion. These effects are not philosophical suggestions. They have been measured with clocks, observed around stars, and incorporated into technologies such as satellite navigation. Once space and time become dynamic rather than fixed, the possible shapes of reality become far richer than everyday experience suggests. One of the most surprising lessons of curved geometry is that the size of an interior does not always correspond neatly to the size of its boundary. In ordinary life, a small box contains a small volume, while a large box contains a larger one. But in strongly curved spacetime, this intuition can fail. A surface with a modest area may enclose a region whose internal geometry is extraordinarily extended. From the outside, the object may appear compact. From within, distances may unfold in ways an external observer could never guess. This does not automatically prove that hidden universes exist, but it creates the mathematical room in which such ideas can be considered seriously. Black holes provide the most dramatic example. A black hole forms when matter becomes compressed so intensely that spacetime develops an event horizon. This horizon is not a solid surface. It is a boundary in cause and effect. Once something passes inward across it, no signal travelling at or below the speed of light can return to the external universe. To someone watching from far away, the black hole may be described by only a few measurable properties, such as its mass, rotation, and electric charge. Yet the space-time behind the horizon may possess a complex interior that remains permanently hidden from the outside. In the simplest textbook descriptions, matter falling into a black hole eventually reaches a singularity, a place where the equations of general relativity predict extreme curvature and cease to provide a reliable physical description. Most physicists do not interpret this breakdown as proof that nature literally contains a point of infinite density. Instead, it is usually taken as evidence that general relativity is incomplete in such extreme conditions. A deeper theory combining gravity with quantum mechanics would be needed, until such a theory is confirmed. We cannot say with certainty what happens at the deepest interior of a black hole. That uncertainty leaves open several possibilities, though none has yet been established by observation. Some theoretical models replace the singularity with a bounce, a transition, or another expanding region of spacetime. In these ideas, matter, collapsing into a black hole, might not end at an infinitely compressed point. Instead, under conditions where quantum gravity becomes important, the collapse could reverse or connect to a new domain. From the viewpoint of that domain, the event might resemble the beginning of an expanding universe. The new region could grow internally while remaining hidden behind the parent black hole's horizon. To observers outside, there would be only a dark, compact object. To hypothetical observers inside, there might be an immense cosmos with its own stars, galaxies, and passage of time. It is important to rest here for a moment and separate possibility from evidence. General relativity permits many mathematical spacetime solutions, but not every solution must occur in nature. Some are unstable. Some require unrealistic conditions. Others may disappear when quantum effects are treated correctly. The idea that black holes could contain new universes is therefore speculative. It is not an accepted explanation of what lies inside real astrophysical black holes. Scientists explore it because the mathematics of gravity allows strange interior structures, and because singularities signal that our current theories cannot tell the complete story. The hypothesis is scientifically interesting precisely because its status remains uncertain. There are also other ways in which a universe might be hidden within ours. It might not be enclosed by a black hole at all. It could occupy dimensions that ordinary matter does not enter. It could consist of particles interacting through forces invisible to us. It could resemble a parallel quantum history rather than a separate region of space. Each of these possibilities comes from a different area of theoretical physics, and they should not be blended into one vague idea. A hidden dimension is not the same as a baby universe. A dark sector is not the same as another branch of quantum reality. Yet all of them challenge the assumption that everything real must be directly visible. Visibility is a surprisingly narrow standard. Human eyes detect only a small band of electromagnetic radiation, radio waves, infrared light, Ultraviolet light, X-rays, and gamma rays remained invisible to us until instruments extended our senses. Neutrinos pass through our bodies in enormous numbers while rarely interacting. Dark matter, whatever it is, appears not to emit ordinary light at all. Yet its gravitational influence shapes galaxies. Nature has repeatedly shown that existence does not depend on being obvious to human perception. A second universe, if one existed, might remain hidden not because it was distant, but because the channels connecting it to us were extremely weak or entirely absent. Imagine two vast orchestras playing in the same concert hall, were each producing sound at frequencies the other cannot detect. Their musicians share the room, yet neither hears the other's music. Only a slight vibration in the floor occasionally reveals that another performance is taking place. Some hidden sector theories resemble this picture. Ordinary particles may belong to one collection of forces, while unknown particles belong to another. Gravity, because it responds to energy and mass more universally, might provide the faint vibration linking them. Such a hidden world would not necessarily be a complete universe in the cosmological sense, but if it contained many particles, force, structures, and perhaps its own complex history, the difference could become partly a matter of definition. The deeper problem is that the word inside may not behave as simply as we expect. We usually think of one thing being inside another as a smaller object contained within a larger volume, like a stone inside a bowl. But in modern physics, inside can refer to causal separation, mathematical embedding, hidden degrees of freedom, or an interior region whose geometry expands independently. A universe inside ours might not occupy a small location that a spacecraft could visit. It could be separated by a horizon, present throughout space in an unseen form, or connected only through conditions that existed during the earliest moments of cosmic history. So our journey begins not with an answer, but with a change in perspective. The universe we observe may be only one layer of a deeper reality. Its visible galaxies, glowing stars, drifting planets, and vast dark spaces could belong to a structure containing regions that no telescope can reveal directly. Physics does not yet tell us that a second universe is hidden here. It tells us something subtler: the geometry of spacetime, the limits of observation, and the unfinished union of gravity with quantum theory prevent us from confidently declaring that no such universe could exist. And somewhere within that quiet uncertainty, the mystery begins to open. To understand how an entire reality might remain hidden inside our own, we must move closer to one of the strangest boundaries in nature, the event horizon of a black hole. An event horizon is not made of matter, and it is not a glowing shell or a physical wall. It is a boundary created by the shape of space-time itself. Beyond it, every possible path into the future leads farther inward. Light may still move locally at its usual speed, but the geometry offers no outward route that reaches the distant universe. In this sense, the horizon does not imprison objects by force. It removes escape from the map of possible futures. From far away, a black hole can appear deceptively simple. Astronomers may estimate its mass by watching nearby stars orbit it, measure its rotation through the behavior of surrounding gas, and sometimes infer its size from the shadow it casts against glowing material. The radius of a non-rotating black hole's event horizon grows in proportion to its mass. A black hole with several times the mass of the Sun may have a horizon only a few tens of kilometers across, while the enormous black holes at the centers of galaxies may possess horizons millions or billions of kilometers wide. Yet even these outer measurements tell us almost nothing about the true spatial structure hidden behind the horizon. The common image of a black hole as a dense ball with an empty darkness around it is misleading. According to general relativity, the horizon encloses a region of space-time, not merely a compact lump of matter. Once inside, the distinction between moving through space and moving toward the future becomes strangely altered. Outside the horizon, you may choose to travel inward or outward, though gravity may make one direction difficult. Inside, progressing towards smaller radial distances becomes as unavoidable as progressing toward tomorrow. You cannot simply stop and hover, because all future directed paths carry you deeper. The interior is therefore not merely a location. It is a different causal arrangement of space and time. Imagine floating far from a quiet, isolated black hole while a small robotic probe falls toward it. From your distant perspective, light from the probe becomes increasingly red and faint. Its signals arrive more slowly. Stretched by the intense gravitational field, you never receive a final message announcing the exact instant it crosses the horizon. Instead, the probe appears to fade toward darkness. But from the probe's own perspective, assuming the black hole is large enough and tidal forces are not immediately destructive, the crossing may seem uneventful. There is no solid line painted across space. Locally, the probe continues falling, carrying its clock and its measurements into a region from which its reports can never return. This difference between perspectives is essential. The event horizon is globally significant, yet a freely falling observer may not detect anything unusual at the moment of crossing. The horizon's meaning depends on the future of the entire space-time, and on whether signals can ever reach the outside. It is less like passing through a visible gate and more like crossing a line on a river beyond which every current eventually reaches a waterfall. The water at that line may feel calm. Only the shape of the full landscape reveals that return has become impossible. In the same way, the horizon conceals its deepest consequence from anyone examining only the immediate surroundings. Now consider the interior volume of a black hole. It is tempting to calculate it as though the horizon were the surface of an ordinary sphere. We might take its radius, use a familiar formula, and imagine a finite volume inside. But curved spacetime does not always permit such a simple interpretation. The volume depends on how we choose a slice through spacetime, meaning how we define which distant events count as happening at the same moment. Different choices can produce different descriptions. In some well-studied approaches, the interior volume of an old black hole can become extremely large, even while the area of its horizon remains fixed or changes only slowly. This may sound like a mathematical trick, but it reflects a genuine lesson of relativity. Space is not a rigid container waiting for matter to fill it. Its geometry responds to gravity and can stretch in unexpected ways. A narrow entrance may lead into an extended interior. Much as a long cave might begin with a small opening in a cliff, even that cave analogy is limited, because an ordinary cave exists within a larger three-dimensional space. A black hole's interior is part of spacetime itself, and its hidden extent cannot necessarily be represented faithfully by imagining a room tucked inside a sphere. One useful image is a funnel drawn on a flexible sheet. Although it must be treated carefully, the sheet bends downward as an object approaches the black hole, suggesting a deep gravitational well. Yet a real black hole is not a pit in a separate direction beneath space. The funnel is only a visual aid showing how distances and trajectories may be altered. Still, it hints at how a region can possess much more internal structure than its outer boundary suggests. The entrance may appear finite, while the geometry beyond it stretches farther than ordinary intuition allows. That possibility is one reason physicists have considered whether black hole interiors could shelter regions resembling independent universes. The oldest idealized solutions of Einstein's equations revealed even stranger possibilities. A perfectly eternal, non-rotating black hole can be mathematically extended to include more than one exterior region, connected through a structure sometimes associated with an Einstein-Rosen bridge. In diagrams, the full geometry may appear to link two separate universes, but this elegant construction does not describe the simple passage imagined in popular stories. The bridge closes too quickly for ordinary travelers to cross, and a black hole formed by the collapse of a real star does not necessarily possess the same complete eternal geometry. The mathematics is illuminating, but it should not be mistaken for evidence of a usable cosmic doorway. Rotating black holes introduce further complications. Real astrophysical black holes are expected to rotate because the stars and gas that formed them carried angular momentum. The ideal mathematical description of a rotating black hole contains an outer horizon, an inner horizon, and a more complicated central structure. If the solution is extended without disturbances, it may appear to contain paths toward other regions of spacetime. Yet, realistic black holes are never perfectly isolated. Small amounts of radiation and infalling matter can become enormously amplified near the inner horizon, creating instabilities that may destroy the smooth passages suggested by the ideal equations. Nature often proves less accommodating than the most symmetrical mathematics. These examples reveal both the power and the danger of theoretical exploration. Einstein's equations allow us to map possible geometries, including regions hidden behind horizons and connections between distant domains. But equations alone do not tell us which possibilities survive in the real universe. A physically meaningful solution must arise from plausible initial conditions, remain sufficiently stable, and eventually agree with quantum theory. When one of these requirements fails, a beautiful geometry may remain a mathematical curiosity. For this reason, scientists speak cautiously about universes inside black holes. The idea has roots in serious physics, but the path from possibility to reality is long. The question becomes even more difficult because general relativity predicts its own breakdown inside black holes. Under broad conditions, gravitational collapse leads toward a singularity, where curvature becomes extreme and familiar equations lose their predictive power. The singularity is not simply another hidden room waiting to be explored. It marks the point at which the theory can no longer tell us what follows. If a new universe emerges beyond that regime, its birth would depend on quantum gravity, a theory physicists are still trying to complete. Without such a theory, any description of a bounce, tunnel, or expanding interior remains provisional. Some approaches to quantum gravity suggest that spacetime may not be infinitely divisible. At fantastically small scales, the smooth geometry described by general relativity might be replaced by discrete structures, quantum relationships, or fluctuating configurations. If so, the collapse toward a singularity could be interrupted. Density and curvature might become extremely large without becoming literally infinite. Under certain models, the interior could transition into an expanding phase. The process is sometimes compared to a compressed spring releasing, though the actual mathematics is far more subtle. Such a transition might create a region that grows away from the parent universe while remaining causally hidden behind the horizon. From within that growing region, time and space could be experienced in a way entirely different from the external description. A hypothetical observer born there would not necessarily see a black hole surrounding them. They might observe an expanding cosmos, perhaps beginning from a hot and dense state. The external black hole's small horizon would not function as the walls of their universe. Instead, the horizon would belong to the relationship between the parent region and the new one. The interior universe could become immense according to its own measurements, even though it remained associated with a comparatively compact object when viewed from outside. This idea helps explain why the phrase universe inside a black hole is both suggestive and confusing. The new universe would not sit inside the old one like a marble inside a box. Its interior distances might expand independently. It might develop a long history, while only a limited amount of external time appeared to pass. Depending on the geometry, the connection between the two regions could narrow, change, or become inaccessible. In some models, the child universe effectively separates from its parent while preserving only a causal ancestry. To inhabitants of the parent cosmos, the black hole remains. To inhabitants of the child cosmos, the parent may lie forever beyond an unreachable beginning. Could we enter such a universe by falling into its black hole, even if a child universe existed? The answer would almost certainly not resemble a peaceful journey through a portal. Small black holes produce severe tidal forces near their horizons, stretching objects along one direction and compressing them along another. Supermassive black holes may allow a traveller to cross the horizon before these forces become immediately fatal. But deeper inside, the environment would still become extreme. More importantly, speculative models do not guarantee that a traveller from the parent universe could survive the quantum transition or emerge into the expanding region. The existence of a mathematical continuation does not imply a safe physical route. There is another mystery surrounding horizons: the fate of information. In quantum mechanics, information about the state of a system is generally expected to be preserved. But if matter falls into a black hole, and the black hole eventually evaporates through Hawking radiation, it once appeared that the information might disappear permanently. This conflict became known as the black hole information paradox. Many physicists now suspect that the information is somehow encoded in the radiation or in subtle correlations, but the exact mechanism remains debated. Any proposal involving hidden interior universes must confront this issue. Information cannot simply be sent into an unreachable cosmos without explaining how quantum principles remain consistent. The information problem has encouraged a remarkable shift in how physicists think about interiors and boundaries. Some ideas suggest that the information contained within a region may be represented on its boundary, a principle loosely associated with holography. The famous example comes from black hole thermodynamics, where the entropy of a black hole is proportional not to its interior volume, but to the area of its event horizon. Entropy measures, in a broad sense, how many microscopic configurations may correspond to the same large-scale appearance. The fact that black hole entropy follows area rather than volume hints that spacetime may organize information in ways profoundly different from ordinary containers. If a black hole hides an enormous interior while its information is somehow encoded at the horizon, then the relation between inside and outside becomes even stranger. The interior may be physically meaningful to an infalling observer, yet the external description might account for it using data associated with the boundary. Some theoretical approaches even suggest that space-time geometry could emerge from patterns of quantum entanglement. In that view, the spacious interior might not be fundamental in the way we normally imagine. It could arise from deeper relationships among quantum degrees of freedom. A hidden universe might therefore be concealed not only by distance or gravity, but by the way reality translates between different descriptions. These possibilities do not yet provide a confirmed picture of what lies inside a black hole. Instead, they show why the question remains open. Horizons divide what can communicate from what cannot. Curved geometry allows interiors far larger than their boundaries suggest. Quantum theory raises questions about information that classical relativity cannot answer. And idealized solutions reveal pathways that may or may not survive in nature. Each clue points toward a reality more layered than the simple image of a dark sphere in empty space. For now, the safest conclusion is modest. We know black holes possess horizons. We know those horizons conceal regions no external observer can directly inspect. We know general relativity predicts unusual interior geometries and ultimately reaches conditions where it becomes incomplete. We do not know whether those interiors generate new universes, connect to distant regions, end in a quantum bounce, or take some form not yet imagined. The horizon preserves that uncertainty perfectly. It surrounds the unknown without revealing it, leaving a quiet boundary between the universe we can observe and whatever spacetime may become beyond the reach of light. What if the universe we call home did not begin from nothing, but from the interior of a black hole formed in a larger and older cosmos? This possibility is sometimes called black hole cosmology. It suggests that the Big Bang may not have been the absolute beginning of all existence. Instead, it could have marked the beginning of our particular region of spacetime, born when matter collapsed beyond a horizon somewhere else. From the parent universe, The event might have looked like the formation of a black hole. From within the new region, the same process might have appeared as a rapidly expanding universe emerging from an extremely hot and dense state. This idea begins with a similarity that is easy to notice but difficult to interpret. Both the early universe and the interior of a black hole involve enormous densities, intense spacetime curvature, and conditions under which general relativity predicts a singularity. In standard cosmology, if the expansion of the universe is mathematically traced backward, matter and energy become increasingly compressed until the equations approach a state of extreme density. In a collapsing star, the equations describe matter moving inward toward another singularity. One process appears to expand outward, while the other collapses inward. Yet both lead the theory to a boundary where its familiar description can no longer be trusted. The resemblance does not mean that the Big Bang was simply an ordinary black hole explosion. A black hole expands into nothing around it. Because a black hole does not normally explode, and the universe is not expanding outward from a central point into pre-existing emptiness, cosmic expansion occurs everywhere, on very large scales. Distances between unbound galaxies increase because the geometry of space itself evolves. Every sufficiently distant observer sees other distant galaxies receding, without occupying a unique central location. If our universe formed inside a black hole, its expansion would still need to arise from an internal space-time geometry, not from matter rushing through a hole into a surrounding room. A useful comparison is the surface of an inflating balloon. Although the real universe has 3 spatial dimensions rather than 2, small marks drawn across the balloon move apart as the surface expands. None of the marks is the center of expansion on the surface itself. The balloon has a center only when viewed from the higher dimensional space surrounding it, and that external viewpoint is not part of the 2-dimensional world experienced by the marks. In a similar way, a universe born within a larger structure might have no observable central point from the perspective of its inhabitants, even if its existence were connected to an event in a parent spacetime. The crucial step in many black hole cosmology models is the removal of the singularity. Classical general relativity says that sufficiently complete gravitational collapse leads toward a region where curvature becomes unbounded. But physicists expect quantum effects to become important long before nature reaches a literal infinity. Quantum mechanics often prevents physical systems from being compressed or localized without limit. Atoms resist collapse because of quantum rules. Dense stellar remnants can be supported by quantum pressure until gravity becomes too strong. At even more extreme scales, an unknown quantum theory of gravity may alter spacetime itself and prevent the classical singularity from forming. If collapse does not continue indefinitely, the interior might reach a maximum density and then enter a new phase. In some speculative models, this becomes a bounce. The material that was contracting does not rebound through ordinary surrounding space like a rubber ball striking the floor. Instead, the geometry changes from contraction to expansion. A new direction of time may open toward a growing region. What looked like gravitational collapse from the parent universe could therefore become cosmic expansion on the other side of the transition. The Big Bang would then be replaced by a big bounce. Although the precise mechanism differs greatly among competing approaches, one family of ideas draws inspiration from quantum cosmology, where the entire geometry of the universe is treated as a quantum system. Another relies on modifications to general relativity that become important at extreme density. Some theories include torsion, an additional geometric property associated with the intrinsic spin of particles. Under unusual conditions, torsion could create an effective repulsion and prevent matter from reaching infinite density. Other approaches imagine spacetime as composed of quantum building blocks, allowing an interior to pass through a smallest possible volume before expanding. None of these mechanisms has been confirmed, and they do not all make identical predictions. The parent black hole and child universe would also have a complicated relationship in time. To an external observer, matter, falling toward the horizon, appears increasingly slowed and redshifted, although the black hole itself forms in a finite physical process. Inside, the evolving geometry could support a long, or even effectively independent cosmic history. The child universe might continue expanding long after the black hole in the parent universe had changed, merged with another object, or begun to evaporate. Ordinary intuition expects the contents of something to disappear when its container disappears, but here the word container is misleading. The two regions would be linked through space-time geometry rather than by the walls of a physical vessel. In some versions, the connection between the parent and child becomes a narrow throat that cannot be crossed in reverse. The child universe may pinch away causally, meaning that no message from its expanding interior can return to the parent region. Nor could its inhabitants necessarily travel backward to discover the black hole from which their cosmos emerged. Their earliest observable state would be hot, denser, and rapidly changing. Whatever existed before that state might remain hidden behind the same limits that prevent us from observing conditions before the earliest meaningful moments described by our theories. This raises a natural question. Is there anything in our universe suggesting that it might have such an origin? At present, there is no accepted observational evidence that our cosmos exists inside a black hole. The standard cosmological model describes a universe that evolved from an early hot and dense phase, underwent a brief period of rapid inflation according to the leading framework, and later developed the galaxies and large-scale structure we observe. This model is supported by the expansion of space, the cosmic microwave background, the abundance of light elements, and the distribution of matter. Any black hole origin theory must preserve these successes rather than merely offer an imaginative alternative. Some advocates have explored whether the estimated mass and size of the observable universe could be compared to the properties of a black hole. Such comparisons can produce intriguing numerical relationships, but they must be handled carefully. A homogeneous expanding universe is not the same spacetime as a static object embedded in empty surroundings. Formulas derived for an isolated black hole cannot always be applied directly to the entire cosmos. The universe does not appear to be a conventional black hole with an exterior region we can observe, and cosmic expansion changes the meaning of horizons. A numerical resemblance may inspire a hypothesis without constituting proof. Another possible clue could come from the geometry of space. Measurements indicate that the observable universe is very close to spatially flat on large scales, meaning that familiar geometric rules work remarkably well across immense distances. A child universe emerging from a black hole would need to produce a geometry compatible with this observation. Some models attempt to combine black hole birth with cosmic inflation, the proposed episode of extremely rapid expansion in the early universe. Inflation could smooth curvature, dilute irregularities, and make a small initial region become far larger than the observable cosmos. In such a model, the black hole origin might occur before the inflationary phase we could indirectly test. Inflation itself already allows our visible universe to be only a small part of a much larger domain. It was introduced to explain why distant regions of the cosmos have nearly the same temperature, why space appears so flat, and why unwanted relics are not commonly observed. During inflation, quantum fluctuations may have been stretched to astronomical scales, later becoming the seeds of galaxies. Black hole cosmology does not automatically replace inflation. It may require inflation, compete with it, or attempt to explain what set inflation into motion. The relationship depends on the particular theory, which is one reason broad statements about living inside a black hole can be misleading. The hypothesis also faces a difficult issue involving direction and symmetry. The large-scale universe appears similar in every direction. Apart from small variations in local structure, a black hole formed from collapsing matter in a parent universe might seem likely to carry traces of its formation, such as rotation, asymmetry, or disturbances. Our universe does possess small irregularities, and it may have a very slight global rotation only within tight observational limits. But there is no established pattern pointing clearly to a parent black hole. A successful theory would need to explain why any inherited features became so weak or why they appear in a specific measurable form. There is also the question of conservation. If a new universe forms within a black hole, does it contain more matter and volume than the original collapsing object seemed to possess? From the viewpoint of ordinary space, that might look impossible. Yet, general relativity does not define global energy in every spacetime as simply as classical mechanics does. An expanding universe can acquire enormous internal volume without requiring that volume to be packed inside an equal external volume. Gravitational energy, spacetime curvature, and cosmic expansion complicate the accounting. Still, any complete model must remain mathematically consistent and explain how the properties of the child universe relate to those of its parent. Some versions of the idea imagine a chain of cosmic generations. Stars collapse into black holes. Some black holes give rise to new universes. Those universes form their own galaxies and stars, which later produce more black holes and more descendants. Reality would then resemble a vast branching tree rather than a single isolated cosmos. Each universe might inherit physical laws or constants from its parent, perhaps with slight variations during the extreme birth process. This suggestion has inspired a speculative concept sometimes called cosmological natural selection, in which universes producing many black holes would generate more descendants. The analogy to biological evolution is appealing, but it remains highly conjectural. Natural selection in biology depends on reproduction, heritable variation, and differences in reproductive success. A cosmic version would require universes to reproduce through black holes, transmit physical properties, and vary in ways that influence future black hole production. None of these steps has been experimentally demonstrated. Even if our universe appears well suited to forming stars and black holes, that fact alone does not show that it was selected through cosmic ancestry. The proposal is valuable as an example of how scientists try to transform philosophical questions into models that might eventually produce testable consequences. Testability is the central challenge. A parent universe may be causally inaccessible by definition. If no light, particle, or signal can cross from it into our observable history, how could we ever distinguish a black hole origin from other models of the early cosmos? One possibility would be to identify a unique imprint predicted by the transition, such as a particular pattern in primordial gravitational waves, subtle features in the cosmic microwave background, or limits on the initial density and curvature. But different theories can sometimes produce similar signals, and early universe observations are difficult. A convincing test would require predictions precise enough to separate one model from its rivals. Primordial gravitational waves are especially interesting because they could preserve information from extremely early stages. These waves would be ripples in spacetime generated before stars and galaxies existed. Scientists search for their possible influence on the polarization of the cosmic microwave background and through future gravitational wave observatories sensitive to different frequencies. A quantum bounce or black hole birth might create a background unlike that predicted by conventional inflation. Yet no accepted detection currently reveals such an origin. The absence of evidence does not completely eliminate the idea, but it prevents the idea from being presented as established science. The cosmic microwave background itself is a faint field of radiation released when the universe became transparent roughly hundreds of thousands of years after the hot early phase. It is extraordinarily uniform, with tiny temperature variations that record the seeds of later structure. Researchers have searched this background for unusual alignments, circles, asymmetries, and other signs of physics beyond the simplest model. Some features have generated debate, but none has been confirmed as evidence that our universe formed inside a black hole. Cosmic data contain both real patterns and statistical accidents, and the human mind is naturally skilled at seeing meaning in faint irregularities. Even if the hypothesis remains unproven, it offers a useful lesson about the meaning of beginnings. When we say the universe began with the Big Bang, we do not necessarily mean that all reality emerged from an absolute nothing at a single instant. The Big Bang model describes the evolution of our observable universe from an early, hot and dense condition. As we approach the earliest limits, current theories become incomplete. There may have been inflation, a quantum phase, a bounce, a previous contraction, or some process not yet conceived. A parent black hole is one candidate among many, not a hidden fact waiting to be announced. It also changes the emotional image of a black hole. Instead of representing only destruction, a black hole might, in some models, become a place where one cosmic history ends and another begins. Matter disappearing from one region could contribute to the birth of an expanding spacetime inaccessible from the outside. The same geometry that creates darkness for one observer might create an open future for another. This is not a reason to romanticize black holes or forget their violence. It is a reminder that words such as collapse, ending, and interior may describe only one side of a larger process. If our universe truly existed within a black hole, we might never see its external horizon. It would not appear as a dark sphere surrounding the night sky. Every direction we look would remain part of the internal cosmic geometry. The parent universe would not lie beyond a particular group of galaxies, waiting to be reached with a sufficiently powerful spacecraft. It would belong to a causal past or an external description unavailable from our side. We could measure the contents and evolution of our own cosmos with increasing precision, while still remaining permanently unable to observe the larger setting in which its birth occurred. For now, black hole cosmology rests in the quiet territory between mathematical possibility and physical confirmation. It is motivated by the singularities of general relativity, by the expectation that quantum gravity changes extreme collapse, and by the curious relationship between black holes and expanding universes. It must still overcome major theoretical difficulties and produce evidence distinguishing it from better established cosmological models. Yet it invites us to consider a profound possibility. The universe may be complete from our perspective without being the whole of reality, and its beginning may have been an interior event within a story far older than the one we can see. A hidden universe does not have to be sealed inside a black hole or separated from us by an unreachable region of distant space. It might exist here, throughout the same cosmic volume we inhabit, while remaining almost entirely invisible to ordinary matter. Quantum physics allows reality to be organized in ways that are difficult to picture using familiar objects. Two systems can share the same location yet respond to different forces. Particles may pass through one another without exchanging light. Entire sets of fields may fill space while interacting with our atoms only through gravity or an extremely faint connection. In this sense, another universe could be hidden not because it is far away, but because it speaks a physical language we cannot easily hear. To understand this possibility, it helps to remember that the universe is not fundamentally made of tiny solid beads moving through emptiness. According to modern particle physics, space is filled with fields. An electron is an excitation of an electron field. A photon is an excitation of the electromagnetic field. Other particles arise from other fields extending throughout space. The objects around you appear solid because these fields interact according to precise quantum rules. Electromagnetic repulsion prevents the atoms in your hand from passing freely through the atoms of a table. The strength and variety of these interactions create the visible world. But there is no requirement that every possible field must interact strongly with the ones composing human bodies. The established standard model of particle physics describes the known elementary particles and three fundamental interactions: electromagnetism, the strong nuclear force, and the weak nuclear force. It has been tested with extraordinary precision, yet it does not explain everything. It does not account for dark matter, fully explain the dominance of matter over antimatter, or include a quantum description of gravity. These gaps suggest that additional particles or fields may exist. Some could be extremely massive, others might be very light. Some may have escaped detection because they interact only weakly with ordinary particles. A sufficiently rich collection of hidden fields could behave almost like a parallel physical world, occupying the same space. Physicists sometimes call such a collection a hidden sector or dark sector. The word dark does not necessarily mean cold, evil, or completely empty. It means that the particles do not couple strongly to electromagnetic radiation and therefore do not shine, absorb ordinary light, or reflect it in familiar ways. A hidden sector could contain only one new particle, but more elaborate theories allow several particles and perhaps forces acting only among them. There could be dark equivalents of electrical charge, dark radiation, or stable bound structures. These ideas remain speculative, yet they arise naturally in many attempts to extend known physics beyond the standard model. Imagine standing in a room filled with an invisible gas that passes through walls, bodies, and furniture without friction. You could walk through it without feeling resistance. If the gas also failed to scatter light, no window, camera, or telescope would reveal it. Now imagine that its particles interact strongly with one another, forming currents, clouds, and perhaps complex structures. The gas would possess its own active world while remaining nearly absent from human experience. Only its gravitational pull or an occasional rare collision might betray its existence. A hidden sector could resemble this image, although real quantum fields would not behave exactly like an ordinary gas. Gravity is particularly important because it appears to respond to all forms of energy and momentum. A particle does not need an electric charge to produce gravity. It does not need to emit light. If a hidden sector contained enough mass, its gravitational influence could affect the movement of stars, galaxies, and cosmic structure. This is one reason hidden sector models are often discussed in connection with dark matter. The dark matter inferred by astronomers could be composed of particles belonging to an unseen collection of fields. However, dark matter's existence would not automatically prove the presence of a second universe. It might consist of a single simple particle rather than a complex parallel cosmos. The phrase parallel universe is therefore used carefully in serious physics. A hidden sector occupying our spacetime is different from a separate universe with its own independent space and time. The two sectors would share the same gravitational environment and perhaps the same cosmic origin. Yet if their particles experienced different forces and interacted only faintly, each sector could develop largely independently. Ordinary galaxies might form within one network of matter while dark structures formed within another. They could overlap geographically but remain almost completely separated in their chemistry, radiation, and internal activity. Whether to call the hidden sector another universe would depend more on language than on a sharp scientific boundary. Some models propose a mirror sector in which every known particle has a hidden partner. There might be mirror electrons, mirror proton, mirror photon, and mirror atoms governed by equations resembling those of ordinary matter. This idea has been explored partly because nature displays intriguing patterns and asymmetries. A mirror world could restore certain symmetries at a deeper level, even if our visible sector appears unbalanced. Such theories do not claim that a duplicate Earth is silently occupying the room around us. The distribution, temperature, and cosmic history of mirror matter could differ greatly from those of ordinary matter, and no confirmed evidence currently establishes that a full mirror sector exists. If mirror atoms were present, they might form mirror gas, stars, or compact objects that emit mirror light rather than ordinary light. Our telescopes would not directly detect that radiation because our instruments are made from ordinary charged particles. We might observe only gravitational effects, such as unexplained motions or invisible masses bending the light of background objects. Yet a universe containing large numbers of hidden stars would face observational limits. Its gravitational behavior, influence on galaxy formation, collision, and early universe radiation would need to match what astronomers already measure. The freedom to imagine hidden worlds is constrained by the visible cosmos with increasing precision. Another possibility involves extra-spatial dimensions. We experience 3 dimensions of space: length, width, and height. Certain theories attempting to unify gravity with quantum physics introduce additional dimensions that may be curled up at extremely small scales or structured in ways inaccessible to ordinary motion. A creature living on a thin surface might know only directions along that surface while remaining unaware of a larger surrounding dimension. Similarly, familiar particles could be confined to a 3-dimensional region within a higher dimensional reality. Gravity might extend more broadly, which could help explain why it appears so much weaker than the other fundamental forces. In some higher dimensional models, our observable universe is described as a brane, a lower dimensional surface embedded in a larger space, sometimes called the bulk. Another brane could exist nearby in the higher dimensional direction while remaining unreachable through ordinary travel. It might carry its own particles, force, stars, and cosmic evolution. From our viewpoint, this neighbouring universe would not lie to the left, right, above, or below in any familiar direction. Its separation would occur along a dimension our matter cannot enter. 2 branes could therefore be very close in the higher dimensional geometry, while appearing completely disconnected to observers confined within them. The image of parallel sheets floating beside one another is helpful but incomplete. A brane is not necessarily a material membrane suspended in ordinary space, and the additional dimension need not resemble an open direction through which a spacecraft could simply turn. The physics controlling particles may confine them strongly. Just as light can be guided along an optical fibre without easily escaping, only particular fields, perhaps gravity, might move through the larger space. If another brane influenced ours gravitationally, subtle effects could appear in cosmology or particle experiments. So far, no experiment has confirmed the existence of such an adjacent universe or of accessible extra dimensions. Some speculative cosmological models even imagine collisions between branes. An encounter could release enormous energy and produce a hot, expanding state resembling the beginning of a universe. In that picture, the Big Bang might reflect a collision within a higher dimensional reality rather than an absolute beginning. These proposals were developed as alternatives or extensions to inflationary cosmology, and they attempt to make distinctive predictions about cosmic structure or primordial gravitational waves, yet they remain unconfirmed. Their mathematical richness should not be confused with observational support. The early universe permits many possible stories, but nature has so far revealed only limited clues about which one is correct. Quantum mechanics introduces an entirely different meaning of hidden universes. The equations of quantum theory describe systems through a wave function containing multiple possible outcomes. When a measurement occurs, we observe one definite result. The traditional language of quantum mechanics often says that the wave function collapses to the observed outcome. The many worlds interpretation proposes instead that the full quantum state continues evolving without collapse. Different outcomes become associated with separate branches of the universal wave function. In one branch, a detector records one result. In another branch, it records another. Both remain part of the total mathematical description. These quantum branches are sometimes called parallel universes, but they are not hidden regions located somewhere else in space. They may occupy the same underlying quantum reality while becoming effectively unable to interfere after a process called decoherence. Decoherence occurs when a quantum system interacts with its environment. Information about different possible outcomes spreads into countless particles, making the branches behave independently for practical purposes. A coffee cup does not appear to exist in visibly competing positions because its molecules constantly interact with light, air, and the table beneath it. Any delicate quantum overlap becomes dispersed almost instantly into the environment. In the many worlds view, every quantum possibility with a non-zero amplitude may continue within a branch. This idea can sound dramatic, as though a new universe is created whenever someone makes a choice. That popular image is too simple. Branching is not necessarily triggered by human decisions, and there may be no precise moment when one perfectly defined world divides into two. Quantum interactions occur continuously and involve enormous networks of correlations. The interpretation describes a vast structure of effectively separated histories rather than an endless row of cleanly copied realities. It is one attempt to explain the mathematics without introducing physical wave function collapse. Many worlds is an interpretation, not a separately verified extension of quantum mechanics. It generally produces the same experimental predictions as other interpretations when applied to ordinary laboratory situations. This makes it difficult to test directly. Some physicists find it attractive because it preserves the smooth mathematical evolution of the wave function. Others argue that it creates difficult questions about probability, the meaning of branches, and what should count as an observer. There is no scientific consensus that countless quantum universes literally exist. The disagreement concerns how to understand a theory whose practical predictions have been extraordinarily successful. It is also important not to confuse quantum branches with hidden particle sectors or brane universes. A dark sector could, in principle, produce new experimental signals through particle collisions or gravity. Extra dimensions might alter forces at short distances or influence cosmic evolution. Many worlds may not produce new results beyond standard quantum mechanics because it interprets the same equations differently. These ideas are grouped together in popular discussions because each suggests unseen realities, but scientifically they address separate questions. One concerns unknown matter, another concerns the geometry of spacetime, and another concerns the meaning of quantum measurement. Quantum entanglement adds still another layer to the mystery. Two particles can share a combined quantum state so that measurements of one are correlated with measurements of the other, even when they are widely separated. These correlations do not allow usable information to travel faster than light, but they reveal that quantum systems cannot always be described as independent objects possessing separate properties. Some modern research explores whether spacetime itself may emerge from patterns of entanglement. In such approaches, distance and geometric connection could reflect deeper quantum relationships rather than being fundamental features existing from the beginning. If spacetime emerges from entanglement, then the meaning of a universe may become more abstract. Two regions that appear disconnected geometrically might be related through a deeper quantum description. Conversely, systems sharing the same apparent space might belong to nearly independent networks of interaction. Certain theoretical correspondences suggest that a gravitational universe can sometimes be described by a non-gravitational quantum theory living in fewer dimensions. This holographic behavior does not mean the universe is an illusion or a computer projection. It means that the same physics may have two very different but mathematically equivalent descriptions. Ideas involving wormholes and entanglement have also inspired the suggestion that certain geometric connections may correspond to patterns of quantum correlation. This remains an active and highly theoretical area of research. It does not show that every entangled pair creates a tunnel through which objects can travel. Instead, it hints that geometry and quantum information may be closely related. If that relationship is fundamental, hidden universes might not merely be places obscured behind walls. They could be alternative organizations of information, separated from us by the structure of quantum states rather than by ordinary kilometers. Can any of these possibilities be observed? Hidden sector particles might occasionally interact with ordinary particles in underground detectors, particle accelerators, or precision experiments. Extra dimensions could reveal themselves through deviations in gravity, unusual collision products, or missing energy carried away from familiar fields. Quantum interpretations are harder to distinguish experimentally. Although advances in controlling larger quantum systems continue to test how far superposition and entanglement extend, each investigation asks a slightly different question, but all probe whether visible reality is only one accessible portion of a more extensive physical structure. So far, experiments have not uncovered a confirmed second universe overlapping ours. No mirror star has been identified beyond doubt. No extraspatial dimension has been directly detected. No observation has established that the many worlds interpretation is uniquely correct. Yet the absence of confirmation does not make these ideas meaningless. They provide frameworks for exploring the gaps in current knowledge, and they often suggest measurable consequences that can be ruled out or constrained. Science advances not by treating every possibility as true, but by allowing imagination to enter the mathematics and then asking nature which possibilities survive. Perhaps the quietest lesson of quantum theory is that reality does not have to resemble the world presented by our senses. The solid surfaces, distinct objects, and single histories of daily life emerge from deeper fields. Probabilities and interactions. The hidden universe might be enclosed behind a horizon, but it might also be woven through the same space as our own, separated by forces we do not feel or dimensions we cannot enter. It might even exist as another branch of a quantum state, neither near nor far in the usual sense. The more closely physics examines the foundations of reality, the less certain the word here becomes. If a hidden universe overlaps our own, the most natural place to search may be within the darkness already shaping the visible cosmos. Astronomers have learned that stars, planets, gas, dust, and every familiar atom account for only a small fraction of the matter inferred from gravity. Galaxies rotate as though surrounded by far more mass than telescopes can see. Clusters of galaxies bend background light more strongly than their luminous contents can explain. Across cosmic history, an unseen gravitational framework appears to have guided ordinary matter into the vast web of galaxies, surrounding enormous regions of emptiness. We call this unknown substance dark matter, not because we understand what it is, but because it does not reveal itself through ordinary light. The case for dark matter does not rest on a single mysterious observation. It appears across many different scales and through several independent methods. Stars far from galactic centers often orbit faster than expected if visible matter supplied all the gravity. Galaxies inside clusters move as though held together by a much larger invisible mass. Gravitational lensing reveals concentrations of matter by measuring how spacetime bends light passing nearby. The cosmic microwave background and the large-scale distribution of galaxies also fit a universe containing a substantial amount of non-luminous matter. Together, these clues form a consistent pattern, although they do not tell us which particle or physical system creates it. Dark matter is often imagined as a cold, thin mist surrounding galaxies, but this picture is only partly useful. It does not seem to form ordinary clouds, shining stars, rocky planets, or biological chemistry, because it does not appear to interact electromagnetically in the familiar way. It can pass through ordinary matter with little resistance, allowing large halos to spread far beyond the bright disks of galaxies. Yet dark matter is not evenly distributed. Gravity gathers it into structures, and those structures influence where normal gas falls and where galaxies emerge. In a sense, much of the visible universe grew inside an invisible architecture that had already begun forming before many stars existed. The simplest models treat dark matter as one new kind of particle, interacting mainly through gravity and perhaps the weak nuclear force. For many years, physicists searched intensely for hypothetical weakly interacting massive particles, often called WIMPs. Such particles could have been produced abundantly in the early universe and later remained as a stable cosmic population. Sensitive detectors have been placed deep underground to shield them from ordinary radiation, waiting for the faint recoil of an atomic nucleus struck by a passing dark matter particle. Particle colliders have also searched for missing energy that might indicate an invisible particle escaping the detectors. So far, no universally accepted direct detection has emerged. The absence of a confirmed signal has not eliminated particle dark matter. It has instead widened the field of possibilities. Dark matter could be much lighter or heavier than early searches assumed. It might interact too weakly for current instruments, or its local density and speed distribution might differ from simplified expectations. Candidates include axions, sterile neutrinos, primordial black holes within restricted mass ranges, and many other hypothetical objects. Each possibility has different consequences for galaxies, stars, laboratory experiments, and the early universe. The search has become less like looking for one expected visitor and more like listening across a broad range of frequencies for something whose voice remains unknown. Among these possibilities lies a more expansive idea. Perhaps dark matter is not a single silent particle, but an entire hidden sector. Ordinary matter contains a surprising variety of ingredients: electrons, quarks, neutrinos, photons, and nuclear forces combine to create atoms, chemistry, stars, oceans, and living cells. There is no fundamental rule saying that the invisible matter must be simpler. A dark sector might contain several particle species, its own charges, and forces that do not act directly on ordinary atoms. If so, what we call dark matter could be the gravitational shadow of a physical world, much richer than the featureless halos usually drawn around galaxies. A hidden sector could contain a force similar in some mathematical respects to electromagnetism. Carried by a hypothetical dark photon, dark particles might attract or repel one another, exchange energy, and form bound states. There could be dark atoms composed of oppositely charged hidden particles, just as ordinary atoms contain positively charged nuclei and negatively charged electrons. Depending on the strengths and masses involved, hidden matter might cool, collapse, or form disks and compact objects. These ideas remain theoretical, and observations already limit how much dark matter can behave this way. Still, a smaller interacting component could remain concealed within a larger, more weakly interacting population. This distinction matters because ordinary matter forms complex structures by losing energy. A cloud of visible gas can radiate light, cool, and contract under gravity. As it becomes denser, it may form stars and planetary systems. Dark matter in the standard model cannot easily shed energy, so it remains in broad, roughly spherical halos rather than collapsing into thin galactic disks. But if some dark particles could emit dark radiation, their behavior might be very different. They could cool through invisible processes and settle into structures overlapping the Milky Way. We might pass through a dark disk, dark clouds, or even hidden compact objects without seeing them directly, noticing only subtle gravitational effects. The phrase dark star is sometimes used in several different ways, so caution is needed. In one speculative scenario, a star made primarily from hidden sector matter could shine by emitting radiation that ordinary telescopes cannot detect. In another, an early object made from ordinary gas might be powered temporarily by dark matter annihilation rather than nuclear fusion. These are distinct ideas, and neither has been conclusively observed. A hidden sector star could still influence neighbouring objects through gravity, perhaps revealing itself through lensing or the motion of visible companions. Yet distinguishing such an object from a dim, ordinary star, a black hole, or another compact body would be difficult. Could a dark sector develop planets, chemistry, or life? Physics cannot currently provide a confident answer. Complexity requires more than multiple particles. Stable structures need suitable forces, energy differences, long-lived environments, and mechanisms that allow matter to organize without immediately collapsing or dispersing. Ordinary chemistry depends on the particular masses and charges of electrons and nuclei, as well as the quantum behavior of electromagnetic bonds. A hidden sector with different constants might form only simple states, or none at all. Another set of parameters might permit intricate structures. Without evidence for the underlying particles, any discussion of dark civilizations would move far beyond what present science can support. Still, the possibility is conceptually striking. An active hidden environment might occupy the same galaxy as Earth while remaining almost completely isolated. A dark object could pass through the solar system without producing light or colliding significantly with planets. If dark matter interacts only gravitationally, it would move through Earth as though our planet were nearly transparent. Its presence would contribute an extraordinarily small gravitational influence compared with Earth's own mass. There is no evidence that a hidden planet is sharing Earth's orbit or that invisible beings surround us. The broader scientific idea is quieter. Complex unseen structures are not logically forbidden, though observations place meaningful limits on how abundant they could be. Galaxy collisions provide one way to study whether dark matter interacts with itself. When clusters collide, their galaxies usually pass through one another because stars are separated by enormous distances. Hot, ordinary gas, however, collides, slows, and produces X-rays. Gravitational lensing can then reveal where most of the mass resides. In several famous systems, the inferred dark matter appears to remain closer to the collisionless galaxies than to the slowed gas. This supports the view that dark matter does not interact strongly in the same way ordinary gas does. Yet small self-interactions remain possible and may even help explain certain details of how mass is distributed inside galaxies. If dark matter particles scatter from one another gently, their halos might develop smoother central regions than completely collisionless models predict. Astronomers compare simulations with the motions of stars and gas in dwarf galaxies, spiral galaxies, and clusters. The interpretation is challenging because ordinary processes such as stellar explosions can also rearrange matter. A galaxy is not a clean laboratory. It evolves through mergers, star formation, radiation, magnetic fields, and feedback from black holes. These overlapping effects make it difficult to determine whether an unusual dark matter distribution reveals new particle physics or merely the complicated history of visible matter. The early universe offers another powerful test. When the cosmos was young and hot, particles interacted in a dense environment that left lasting signatures. Additional hidden radiation could have altered the expansion rate during the formation of light elements or changed the pattern of fluctuations in the cosmic microwave background. Dark particles interacting too strongly with ordinary particles might have erased small structures or shifted acoustic patterns in detectable ways. Because these observations agree reasonably well with a relatively simple cosmological model, any hidden sector must fit within narrow boundaries. It may be rich, but it cannot behave arbitrarily without disturbing the universe we already measure. One possible connection between the visible and hidden sectors is known as a portal. The term does not describe a doorway through which a person could walk. It refers to an allowed interaction linking known particles with hidden ones. A Higgs portal might connect through the Higgs field. A vector portal could involve mixing between the photon and a dark photon. A neutrino portal might link hidden particles with neutrinos. These interactions could be extremely weak, but they offer experimental opportunities. Hidden particles might be produced in accelerators, alter the decay of familiar particles, or create rare signals in precision detectors. The portal would be a mathematical bridge, faint enough to preserve the hidden world's invisibility. Gravity itself may be the only portal, and that would make detection especially difficult. Every form of matter and energy influences spacetime, but gravity is extraordinarily weak at the scale of individual particles. A dark sector connected solely through gravity could remain inaccessible to conventional detectors indefinitely. We would infer its existence through the collective motion of astronomical objects rather than through direct collisions in a laboratory. This is already how dark matter is known today. We see the choreography without seeing the dancers, reconstructing an unseen mass distribution from the paths of stars, gas, galaxies, and light. Yet even gravity may carry more information than total mass alone. The shape of a dark halo, the distribution of small satellite galaxies, the rate at which structures formed, and the behavior of merging clusters can all reveal properties of the hidden matter. Warm dark matter would move rapidly enough in the early universe to suppress the formation of very small structures. Fuzzy dark matter made from extremely light particles could behave like a wave across galactic scales, producing distinctive cores or interference patterns. Self-interacting dark matter could redistribute density through collisions. Each model leaves a slightly different fingerprint on the cosmic web. Astronomers therefore use the universe itself as a vast detector. They map streams of stars pulled from small galaxies and globular clusters, looking for gaps caused by invisible clumps passing nearby. They study gravitational lenses for tiny distortions produced by dark substructure. They measure the rotation of gas and stars near galactic centers. They count dwarf galaxies and compare them with simulations. No single observation is likely to reveal a complete hidden sector, but many carefully combined measurements could narrow its possible properties. The task resembles identifying an unseen landscape by watching how wind moves through trees spread across an entire continent. Primordial black holes provide a different possibility. They would not be made from unknown particles but could have formed from unusually dense regions in the early universe. Depending on their masses and abundance, they might contribute some fraction of dark matter. Searches examine gravitational lensing, the motions of stars, the cosmic microwave background, gravitational waves, and the effects of black hole evaporation. Observations have ruled out many mass ranges as the sole explanation for dark matter, while leaving narrower windows and partial contributions under investigation. If primordial black holes exist, they would represent hidden compact objects rather than a parallel particle world. There is also a radical alternative. Perhaps dark matter does not exist as a substance at all, and gravity behaves differently from current theories on galactic scales. Modified gravity proposals attempt to explain some observations by changing the relationship between visible matter and gravitational motion. Certain approaches reproduce regularities in galaxy rotation with impressive economy, but matching the full range of evidence from galaxy clusters, lensing, the cosmic microwave background, and large-scale structure is difficult. Some models introduce additional fields that effectively behave like unseen matter. The debate remains active, though the dominant cosmological framework continues to include dark matter because it explains many observations together. This uncertainty is scientifically healthy. Dark matter is supported as a gravitational phenomenon, but its microscopic identity remains unknown. Calling it matter reflects the most successful current interpretation, not a direct photograph of the substance. It could be one particle, many particles, compact objects, a modification of gravity, or a combination of effects. A hidden universe is among the more elaborate possibilities and therefore carries a greater burden of evidence. The richer the proposed dark world becomes, the more predictions it should make about structure, radiation, collision, or laboratory experiments. Complexity cannot remain entirely invisible without becoming difficult to test. Suppose, for a moment, that a genuine dark cosmos does coexist with ours. Its history would have begun in the same early universe. Unless it originated through some separate process, as space expanded and cooled, hidden particles might have combined, separated, or undergone phase transitions. Dark radiation could have filled the cosmos before fading into a cold background. Hidden matter might have gathered around the same gravitational wells that attracted ordinary gas. causing two kinds of structure to grow together. A visible galaxy and a dark galaxy could overlap, each shaping the other through gravity while remaining silent across every other channel. The night sky would then be only one layer of a double landscape, where we see the Milky Way's luminous band. Another structure might extend through and beyond it. Its forms might be broad and diffuse, or concentrated into invisible knots. Its internal events could release dark radiation that passes through every telescope untouched. From the hidden sector's perspective, ordinary stars might appear only as gravitational disturbances. Earth itself might be known, if anything could know it, only as a small concentration of mass moving around a larger one. Neither side would see the other's light, yet both would curve the same spacetime. No observation currently requires such a richly populated shadow universe. The standard picture of mostly cold, weakly interacting dark matter remains consistent with a wide range of data, but science has not yet determined whether that darkness is simple or complex. The difference is profound. A single stable particle would add one new ingredient to physics. A hidden sector with forces and structures would reveal that the familiar universe is one ecosystem among at least two, sharing gravity but little else. The same unexplained pull keeping galaxies together could become the first faint evidence of an unseen cosmic history unfolding beside our own. For now, dark matter remains a presence without a face. It gathers galaxies, bends light, and shapes the oldest visible patterns in the universe. Yet it does not announce what it is. Every orbit, influenced by an invisible halo, is a quiet reminder that most matter cannot be examined through ordinary sight. Whether this hidden mass is simple, complex, or evidence that our understanding of gravity is incomplete, it marks a boundary between what the cosmos clearly does and what we can presently explain. Behind that boundary, the idea of a second universe continues to wait. Not proven, but not entirely excluded. If a second universe is hidden inside or alongside our own, how could we ever know that it exists? The question seems almost contradictory. A universe perfectly sealed behind an event horizon, separated by inaccessible dimensions, or disconnected through quantum branching, may leave no message that can reach us. Science depends on observable consequences. So, a hypothesis that can never influence anything we measure cannot easily be distinguished from an idea existing only in imagination. Yet most serious hidden universe models are not completely silent. They may leave indirect traces in gravity, particle behavior, cosmic radiation, or the architecture of space-time. The challenge is to recognize those traces without mistaking ordinary complexity, experimental error, or random patterns for evidence of another reality. The first step is to define what kind of hidden universe we are searching for. A universe beyond a black hole horizon would require different tests from a dark sector overlapping our galaxy. An extra-dimensional brain might alter gravity, while a quantum branch might produce no unique signal beyond the predictions of standard quantum mechanics. Scientists therefore do not build a single detector labeled second universe. They test specific models. Each model must say how the hidden region formed, what laws operate there, how it connects to our world, and what measurable effect should result. Without those details, the phrase hidden universe remains too broad to evaluate scientifically. Gravity is often the most promising messenger because it responds to matter and energy even when light does not. If an unseen region exerts gravitational influence on our universe, astronomers may notice stars moving in unexpected ways, light bending around invisible masses, or galaxies forming differently from theoretical predictions. This is already how dark matter is inferred. But unexplained gravity alone would not demonstrate the existence of another universe. It might indicate an unknown particle, a population of black holes, an error in estimating visible matter, or an incomplete theory of gravity. Evidence becomes compelling only when a particular hidden world model explains several observations more accurately than its alternatives. Gravitational lensing offers one especially gentle way of seeing what does not shine. When light from a distant galaxy passes near a concentration of mass, spacetime curves its path. The background galaxy may appear stretched, magnified, multiplied, or distorted into an arc. By measuring these distortions, astronomers reconstruct the distribution of mass between the source and Earth, including mass that emits no light. Small hidden structures may create subtle anomalies in strongly lensed images. Future surveys could map these effects with increasing precision, revealing whether invisible matter gathers into the smooth halos expected from simple dark matter or into more complicated structures, suggesting internal interactions. Streams of stars around the Milky Way provide another kind of detector. These long, narrow trails form when a small galaxy or star cluster is gradually pulled apart by our galaxy's gravity. If an invisible compact object passes through a stream, it may disturb the stars and leave a gap or bend. By studying many streams, astronomers hope to count dark clumps that cannot be seen directly. An unexpected population of invisible objects might support certain dark matter models, including compact hidden bodies or dense structures within a dark sector, yet visible molecular clouds, ordinary stellar remnants, and uncertainties in the Milky Way's gravitational field can create similar disturbances, so careful comparison is essential. Particle experiments search for more direct contact, deep underground. Detectors contain carefully purified materials protected from cosmic rays and environmental radiation. Scientists wait for an atomic nucleus or electron to recoil in a way that could be caused by a passing dark particle. The expected events are rare, and ordinary backgrounds can imitate them. Natural radioactivity, stray neutrons, neutrinos, and electronic noise must be understood with extraordinary care. A convincing discovery would require a signal that repeats, follows predicted patterns, appears in independent experiments, and resists every known explanation. Even then, detecting one new particle would reveal hidden physics, not automatically an entire second cosmos. Particle colliders pursue the mystery from another direction. They accelerate known particles to high energies and collide them, briefly recreating conditions not seen naturally since the early universe. Hidden particles might be produced in these collisions, but escape the detectors without interacting. Scientists would infer their presence from missing momentum or missing energy, much as one can deduce an unseen object by noticing that visible pieces do not balance. The difficulty is that known particles such as neutrinos also escape detection, and imperfect measurements can create apparent imbalances. Researchers, therefore, search for detailed patterns predicted by specific models rather than treating every missing energy event as evidence of a hidden world. Precision measurements may be even more sensitive than dramatic collisions. Some hidden fields could slightly alter the magnetic properties of particles, the decay rates of unstable atoms, the behavior of neutrinos, or the strengths of familiar forces. Atomic clocks can compare the passage of time with remarkable accuracy. Interferometers can detect tiny changes in distance or phase. Experiments test whether fundamental constants remain stable and whether gravity follows the expected inverse square behavior at very short distances. A hidden dimension, light field, or weak portal might produce a minute deviation. Such measurements rarely attract the same attention as giant telescopes, but they can quietly eliminate broad classes of theories. Extra dimensions might also reveal themselves through gravity. In ordinary three-dimensional space, the gravitational influence of an isolated mass weakens according to a familiar geometric rule. If gravity spreads into additional dimensions at sufficiently short scales, that rule could change. Laboratory experiments use delicate balances and suspended masses to test gravity across tiny separations. So far, no confirmed deviation has demonstrated an extra dimension. Collider experiments also look for unusual resonances. missing energy, or hypothetical partner particles associated with higher dimensional theories. Each non-detection narrows the range of possible dimensions, although sufficiently small, curved, or weakly connected dimensions may remain beyond current reach. Cosmology allows hidden physics to be tested across enormous spans of time. The early universe was hot enough that particles and radiation influenced one another before stars existed. Additional hidden species could have changed the rate of cosmic expansion, altered the creation of light elements, or modified the pattern of the cosmic microwave background. Scientists compared detailed observations with models of the young universe, asking how much unseen radiation or interacting matter could have been present. Because several independent measurements agree surprisingly well, new sectors cannot be added freely. A hidden world must fit inside a narrow observational landscape without disturbing successful explanations of helium, deuterium, cosmic structure, andonscient radiation. The cosmic microwave background is especially valuable because its faint variations preserve information about the universe before galaxies formed. Tiny differences in temperature and polarization reveal the motion of early matter, the geometry of space, and the initial distribution of density. A hidden sector interacting with ordinary matter or radiation could shift the sizes and heights of characteristic patterns in this background. A cosmic bounce, brain collision, or unusual pre-Big Bang phase might also leave a distinctive feature. Yet the signal has travelled for almost the entire history of the universe, and later effects can modify it. Anstrimon noise, galactic dust, and statistical coincidence complicate every search. Scientists sometimes investigate unusually large cold regions, alignments, or circular patterns in the microwave background as possible traces of events beyond conventional cosmology. These features may inspire ideas about collisions with other universes, ancient black hole processes, or structures existing before inflation. But isolated anomalies are dangerous foundations for major claims. In a sky containing millions of measured fluctuations, some patterns will look remarkable by chance. A feature noticed after examining the data may appear more significant than it truly is, because researchers did not predict its exact form beforehand. Strong evidence requires a clear theoretical prediction confirmed through new observations, not merely an interesting shape discovered retrospectively. Primordial gravitational waves could carry information from even earlier times. Unlike light, which could not travel freely through the hot plasma of the young universe, gravitational waves may have moved through matter with little disturbance. Different cosmic origin models predict different wave strengths and frequency patterns. Inflation, phase transitions, cosmic strings, quantum bounces, and brain interactions could each contribute distinct signals. Scientists search through microwave polarization, pulsar timing, ground-based interferometers, and propose space observatories. A detected background would be an extraordinary discovery, but interpreting its source would require caution because several physical processes may produce overlapping signatures. Black holes themselves may provide indirect clues about hidden interiors. Observations of matter falling toward a black hole reveal the behavior of space-time outside the horizon. Gravitational waves from merging black holes allow scientists to test whether the resulting object rings down according to general relativity. Any consistent deviation could suggest exotic compact objects, modified gravity, or unusual horizon-scale physics. Yet the horizon prevents us from receiving direct information from the deep interior. Even a perfectly measured exterior may not reveal whether the black hole ends in a singularity, undergoes a bounce, or generates a child universe. Different interiors can sometimes produce nearly identical outward behavior. Hawking radiation could, in principle, carry subtle information about black hole quantum physics. According to quantum field theory in curved spacetime, black holes should emit extremely faint thermal radiation and gradually lose mass. For astrophysical black holes, This radiation is far colder than surrounding cosmic backgrounds and cannot currently be isolated. Tiny hypothetical primordial black holes would radiate more strongly, but none has been conclusively detected. If future observations reveal detailed departures from a perfectly thermal spectrum, they might illuminate how information escapes and whether hidden interior structures affect the process. Such a measurement, however, remains far beyond present capabilities for known black holes. Researchers also study hypothetical white holes, objects that can emit matter but cannot be entered from the outside. They appear in certain mathematical extensions of black hole solutions and sometimes play a role in bounce models. A collapsing black hole might, under speculative quantum effects, transition into a white hole-like phase. If so, there could be delayed bursts, unusual compact remnants, or other signals. No confirmed astronomical object has been identified as a white hole. Many proposed signatures overlap with ordinary explosions, neutron star activity, or black hole accretion. The theory must therefore become precise enough to predict something nature cannot easily imitate through established processes. A hidden universe connected through a wormhole could create different observational effects. A wormhole is a hypothetical shortcut joining distant regions of spacetime. In classical general relativity, traversable wormholes usually require unusual forms of energy to remain open, and no evidence shows that macroscopic versions exist. An object resembling a black hole but lacking an ordinary horizon might cast a slightly different shadow or produce distinct gravitational wave echoes. Researchers have explored such possibilities, but apparent echoes in data remain debated and may arise from noise or imperfect modelling. Extraordinary geometry demands unusually reliable evidence before it can be accepted. Astronomers may also search for unexplained gravitational influences on the expansion of the universe. If another brane or higher dimensional region interacts with ours, cosmic expansion could differ subtly from the predictions of ordinary general relativity. The rate at which galaxies separate, the growth of large-scale structure, and the relationship between distance and redshift would carry clues. Measurements of supernovae, galaxy clustering, weak lensing, and the cosmic microwave background already constrain these models. Yet cosmology contains difficult uncertainties, including the nature of dark energy, the behavior of neutrinos, and the influence of galaxy formation. A hidden universe would need to emerge from this crowded field of explanations. Quantum branches present perhaps the hardest challenge. If the many worlds interpretation makes the same laboratory predictions as other interpretations of quantum mechanics, no experiment may uniquely prove that other branches exist. Experiments can confirm superposition, interference, entanglement, and decoherence, but these phenomena are accepted across several interpretations. As scientists control increasingly large quantum systems, they may demonstrate that quantum behavior extends farther into the macroscopic world than expected. This would strengthen the universality of quantum mechanics, but it would not necessarily select many worlds over competing views. The debate may remain partly about which description of the same mathematics is most coherent. This raises a philosophical boundary within science. A theory gains strength by making risky predictions that could prove it wrong. If two theories predict exactly the same observations forever, experiment cannot choose between them. Scientists may still compare their simplicity, consistency, explanatory power, or compatibility with deeper theories, but the conclusion will be less direct. Some hidden universes may therefore remain scientifically meaningful as parts of broader mathematical frameworks while resisting isolated confirmation. The inability to observe something directly does not make it false, but it limits how confidently science can speak about its physical reality. There is also the possibility of false discovery. Human beings are naturally drawn to mysterious signals, unexpected lights, unusual particles, and patterns that appear to challenge everything known. But instruments malfunction, data pipelines introduce errors, and statistical fluctuations can look persuasive. History contains many anomalies that weakened as measurements improved. A responsible search for hidden universes must therefore move slowly. Researchers repeat experiments, exchange data, test alternative explanations, and ask whether a claimed effect appears under different conditions. Caution is not the enemy of discovery. It is the method by which a genuine discovery is separated from the many convincing illusions that surround it. The ideal evidence would connect several scales at once. A new particle detected underground might possess properties matching an unexplained collider signal. The same particle could produce the correct dark matter abundance in early universe calculations and explain a distinctive pattern in galaxy structure. A model involving a hidden sector might predict all these effects using one consistent set of parameters. Agreement across independent observations would be far stronger than a single anomaly. Science often advances when phenomena once treated separately become parts of one explanation. As electricity, magnetism, and light were eventually understood as expressions of the same electromagnetic field. A child universe inside a black hole may be much harder to verify because the event horizon blocks direct communication. Its best evidence might come from a complete theory of quantum gravity tested elsewhere. Suppose a future theory accurately predicts black hole behavior, early universe observations, particle interactions, and gravitational phenomena. If that same theory unavoidably implied that black hole interiors produce expanding regions, the case for child universes would become stronger, even without a message arriving from one. The inference would resemble our confidence in inaccessible stellar interiors, which rests on theories tested through their visible consequences. Yet the chain of reasoning would need to be exceptionally secure. Technology will expand the search in ways difficult to predict. More sensitive gravitational wave detectors may listen across wider frequency ranges. New telescopes will map dark matter through billions of galaxies. Precision clocks may detect subtle variations in fundamental fields. Quantum sensors may reach interactions too weak for present instruments. Particle experiments may explore energies and decay processes not previously accessible. Each advance will either uncover something unexpected or narrow the possible hiding places. A second universe may not suddenly appear as a clear image. Its presence, if real, could emerge slowly from a pattern of small inconsistencies, becoming one coherent story. It is equally possible that every search will continue to support a simpler cosmos. Dark matter may turn out to be one stable particle. Black holes may have interiors that do not create new universes. Extra dimensions may be absent or permanently inaccessible. Quantum mechanics may remain open to several interpretations without revealing literal branching worlds. Negative results would still be meaningful. They would teach us which ideas nature does not use and make our picture of reality more precise. The search for a second universe is valuable not only because it might succeed, but because it forces our theories to explain exactly what can and cannot remain hidden. For now, the evidence is incomplete. We see invisible gravity, unfinished theories, inaccessible horizon, and quantum behavior that challenges ordinary intuition. None of these observations proves that another universe exists inside ours. Together, however, they justify asking the question carefully. The task is not to believe every hidden world that mathematics permits. It is to translate each possibility into a measurable consequence and then listen with patience. Somewhere in the faint recoil of a particle, the bending of distant light, the vibration of space-time, or the oldest radiation in the sky, reality may be offering a clue, or it may be quietly telling us that the hidden universe exists only as a possibility we have not yet learned how to rule out. We have travelled through black holes, quantum fields, dark matter, extra dimensions, and the faint traces that unknown realities might leave behind. Yet the deepest part of the mystery is not simply whether another universe exists. It is whether nature would allow creatures inside one region of reality to know that another region is there. Science has expanded human vision far beyond the limits of the eye. But every method still depends on interaction. Something must send light, exert gravity, exchange particles, disturb a field, or leave a pattern in the history of the cosmos. A reality that never touches ours in any measurable way may remain beyond the reach of experiment. No matter how advanced our instruments become, this limit is not caused only by insufficient technology. Some boundaries are built into the structure of spacetime. An event horizon divides events according to whether their influence can ever reach the outside. A cosmic horizon limits the region from which signals can arrive during the history of an expanding universe. If distant space continues expanding in the way current observations suggest, some galaxies that are visible today will eventually become permanently unreachable. Their light will fade, and their future events will never enter our observable world. The universe may contain far more than any civilization, even one surviving for immense spans of time, could ever examine. Horizons teach us that the observable universe is not defined solely by where things are. It is defined by which events can be connected through cause and effect. Two regions may belong to the same overall spacetime while remaining forever unable to exchange messages. Each could contain stars, observer, and long histories, yet neither would become part of the other's experienced reality. From one perspective, the other region would be more than distant. It would be causally absent. This is a strange idea because everyday life trains us to believe that enough time and effort can eventually bridge any physical distance. Cosmology shows that this need not be true. If a child universe formed inside a black hole, its inhabitants might face a similar boundary. The parent cosmos would not be hidden behind dust or darkness that a better telescope could penetrate. It might be excluded from their accessible spacetime altogether. They could develop mathematics describing a possible origin beyond their hot early universe, just as we develop models of what may have preceded our own observable beginning. Their evidence might remain indirect, encoded in broad features of cosmic geometry or in the laws inherited during the transition. They might ask whether their universe was born inside something larger, never knowing that distant thinkers in the parent cosmos had once wondered what lay behind the horizon. This imagined symmetry is humbling. We tend to picture ourselves as observers looking outward upon the universe, as though reality were an object presented for inspection. But we are not outside it. Our bodies, instruments, memories, and ideas are physical processes occurring within the system we seek to understand. Every observation is made from a particular location and time. Every signal reaching us has followed a path permitted by space-time. We cannot step beyond the universe to view its total shape from an external platform. Cosmology is the attempt to reconstruct the largest possible picture while remaining permanently embedded inside one small part of it. The same limitation appears in quantum physics. We never observe a quantum system without becoming physically related to it through measurement. An instrument interacts with a particle. The instrument interacts with its environment, and the result becomes part of a larger chain of correlations. Different interpretations describe this process in different ways, but all agree that observers are not detached spectators. If other quantum branches exist, we may be unable to look across the boundary, separating them, because the very process of decoherence prevents ordinary interference between their macroscopic histories. Their hiddenness would be produced not by a curtain in space, but by the structure of quantum information. A hidden sector presents a more hopeful situation because even a very weak interaction could, in principle, be detected. A dark particle might strike a nucleus once in a great while. An unseen force could slightly change the decay of a known particle. Hidden structures might bend light or disturb streams of stars. Such clues would not immediately reveal a complete shadow cosmos, but they could open a narrow channel between two physical worlds. What began as a tiny experimental anomaly might eventually become a new map of matter, force, and cosmic history. The discovery would resemble opening a window in a room whose walls had previously seemed solid. Yet nature may choose a quieter arrangement. Dark matter could be simple, nearly featureless, and incapable of forming the complex hidden landscapes we imagined. Black holes may not generate new universes. Extra dimensions may exist only at scales so small that they never become habitable domains. Quantum branching may be a useful interpretation without allowing any contact between alternate outcomes. It is important to let the universe remain simpler than our curiosity sometimes desires. Mystery does not guarantee extravagance. The unknown may contain a second cosmos, or it may contain one modest correction to equations we already know. This is why uncertainty should not be treated as a weakness in science. Saying that a possibility is speculative does not dismiss it. It places the idea honestly within the landscape of evidence. Scientific knowledge is not divided only into absolute truth and complete ignorance. Between them lies a wide territory of measured facts, successful models, plausible hypotheses, unresolved tensions, and possibilities that remain mathematically interesting but observationally untested. The hidden universe occupies several places within this territory, depending on what kind of universe we mean. Some versions are natural extensions of established theories. Others require assumptions for which no evidence currently exists. General relativity gives a strong confidence in the existence of black hole horizons and the curvature of spacetime outside them. It gives less confidence about the deepest interior, where quantum effects cannot be ignored. Particle physics describes known fields with astonishing accuracy, yet leaves dark matter unidentified. Quantum mechanics predicts experiments extremely well, but its interpretation remains debated. Cosmology reconstructs the universe's history from ancient radiation, elemental abundances, and expanding galaxies, while approaching an early boundary where tested descriptions become incomplete. The idea of hidden realities grows within these gaps, not because science has failed, but because successful theories reveal precisely where their reach ends. The history of science suggests caution in both directions. Human beings have often imagined invisible realms that did not survive observation. We have also repeatedly discovered that reality contains structures no unaided sense could have anticipated. Microorganisms lived in water before microscopes revealed them. Radio waves crossed rooms before receivers translated them into sound. Neutrinos streamed through Earth before detectors captured their rare interactions. Gravitational waves passed through the planet long before instruments became sensitive enough to measure their tiny stretching of space. What is invisible today may become measurable tomorrow, but invisibility alone is never proof of existence. Perhaps future physics will unite gravity and quantum mechanics in a framework that changes the question entirely. The theory may show that spacetime is not fundamental but emerges from deeper quantum relationships. Black hole interiors and expanding universes might then be recognized as different expressions of one underlying structure. A region that appears separate geometrically could remain connected through information. What we call a universe might become comparable to a phase, a network, or a self-contained pattern within a more basic reality. The phrase inside ours could lose its ordinary spatial meaning. Just as the idea of simultaneity changed when relativity revealed that different observers divide space-time differently. In such a framework, the number of universes might not be a simple count. There may be no clear row of cosmic bubbles that can be labelled 1, 2, and 3. Regions could overlap in one description and separate in another. A child universe might be distinct causally, while sharing a deeper quantum state with its parent. Hidden fields might occupy the same space-time but behave as nearly independent worlds. Quantum branches might resist exact boundaries because branching occurs continuously. The word universe was created for a reality imagined as one complete whole. Modern physics stretches that word until its edges become uncertain. Even so, the question remains valuable because it tests our assumptions. We often assume that a universe must be enormous from every perspective. But curved geometry allows a vast interior behind a limited boundary. We assume that sharing the same space requires frequent interaction. Yet quantum fields can pass through one another almost unnoticed. We assume that every real place should be reachable in principle. While horizons divide spacetime permanently, we assume that a single observed outcome must represent all of reality. Though some interpretations of quantum mechanics preserve many outcomes, each challenge reveals how strongly everyday experience shapes ideas that may not apply at cosmic or microscopic scales. There is a gentle freedom in recognizing these limits. We do not need to force the universe into familiar shapes. A black hole need not be either a simple object or a magical portal. It can be a region whose exterior we understand well and whose interior remains unresolved. Dark matter need not be either a hidden civilization or an imaginary substance. It can be an observed gravitational phenomenon with an unknown microscopic cause. Quantum worlds need not be treated as established copies of our lives or dismissed as meaningless fantasy. They can remain one serious interpretation among several, judged according to mathematical consistency and explanatory value. The search also changes how we think about emptiness. The dark space between stars appears silent, yet it is filled with fields, radiation, particles, gravitational influence, and the expanding geometry of the cosmos. Most of the matter-shaping galaxies cannot be seen. Most locations contain no bright object. But they are not nothing. Even the vacuum of quantum theory possesses structure and fluctuating fields. Though these should not be imagined as ordinary particles constantly appearing in the simple way popular descriptions sometimes suggest, reality is active beneath the threshold of perception, and the visible universe may be only its most luminous surface. If a second universe overlaps ours through hidden fields, then every point in space could belong to more than one physical history. The space inside a quiet bedroom might contain dark matter particles moving through Earth, relic neutrinos from the early universe, electromagnetic fields, gravitational influences from distant galaxies, and perhaps unknown fields with no obvious effect on the listener resting there. Nothing dramatic would need to occur. The layers could coexist without collision, each following its own rules. The hidden universe, if present, might not announce itself with a doorway opening in the sky. It might be inseparable from the calm background of ordinary existence. If another universe lies beyond a black hole horizon, the relationship would be different but equally quiet. Somewhere in the observable cosmos, stars collapse and horizons form. From the outside, matter disappears into darkness, adding mass and rotation to a compact object. Deep within, according to certain unconfirmed models, collapse might avoid a singular end and become an expanding beginning. No flash would reveal this birth to us. The new region could grow without occupying more room in our external space. An entire cosmic future might unfold behind a surface that appears almost perfectly dark. And if our own universe began in such a way, we may carry no obvious memory of the parent. The night sky would not show the larger cosmos outside our horizon. Our laws of physics might be the only inheritance available to examine. Perhaps subtle features in the early universe would preserve a trace. Or perhaps inflation and cosmic evolution erase nearly everything. We might spend centuries refining observations without finding a decisive answer. The absence of access would not make the parent unreal, but it would leave its existence suspended between theoretical necessity and permanent uncertainty. This possibility leads to a difficult but peaceful truth. Reality may be larger than knowledge. Science does not promise that every fact can be discovered by observers in every region. It offers methods for learning from whatever nature allows to interact with us. There may be truths hidden by distance, horizon, quantum separation, or the finite lifespan of civilizations. Acknowledging these limits does not reduce the value of knowledge. It gives knowledge its shape. The visible horizon matters because there is something beyond our view. Whether that something is more familiar space, a separate cosmic domain, or simply a region whose future can never reach us. Humanity occupies a very small physical scale within this mystery. Earth circles an ordinary star in one galaxy among an immense population of galaxies. Our species has existed for only a brief interval compared with cosmic history. Yet, through mathematics, instruments, and shared reasoning, beings formed from local atoms have learned to ask about realities beyond direct perception. We have measured light that travelled for billions of years, detected waves from colliding black holes, mapped invisible mass through gravity, and built experiments sensitive to individual quantum events. Our size does not determine the reach of our questions. There is no need for those questions to end in certainty in order to be meaningful. A map can be valuable even when its edges remain unfinished. Each region of confidence helps define the neighbouring unknown. We know that horizons exist, so we ask what they conceal. We know that most matter is dark, so we ask whether darkness has internal structure. We know quantum theory allows superpositions, so we ask what becomes of unobserved outcomes. We know our cosmological history approaches conditions our current theories cannot describe, so we ask whether another history lies before it. The unanswered question is not a blank space. It is a boundary drawn by what we have already learned. Could there be a second universe hidden inside ours? The honest answer is that physics allows several versions of this possibility, but none has been confirmed. There may be expanding regions behind black hole horizons, hidden sectors sharing our spacetime, neighbouring worlds separated through extra dimensions, or quantum branches inaccessible after decoherence. These are not one theory, and they do not carry equal scientific weight. Some may eventually be ruled out. Others may become parts of a deeper framework. It is also possible that nature contains no second universe in any sense deserving that name. But even if the answer is no, the search has already revealed something profound. Our universe is not the transparent, intuitive stage it once seemed to be. Space and time bend. Horizons conceal futures. Invisible matter shapes galaxies. Quantum systems resist a single classical description. The beginning of cosmic history remains incomplete in our theories. Reality does not owe us simplicity, visibility, or access. It permits us only a local view, then invites us to reason carefully from the traces arriving at our instruments. And if the answer is yes, the second universe may never resemble the dramatic image of another sky waiting beyond a gate. It may be a silent interior unfolding behind a horizon, a dark web woven through our galaxy, or a branch of reality separated from us by quantum history. It may contain no stars, no planets, and no observers. Or it may contain structures more complex than anything we can presently imagine. Until evidence chooses among these possibilities, the most truthful response is neither belief nor dismissal, but patient wonder guided by restraint. Tonight, above every quiet roof and sleeping city, the visible universe continues beyond the reach of the naked eye. Light moves between galaxies. Space-time carries faint vibrations from ancient collisions. Invisible matter gathers around luminous islands of stars. Black holes hold their interiors behind boundaries no message can cross outward. Somewhere within these facts, perhaps, lies another cosmos. Or perhaps the mystery reflects only the depth of the one universe already surrounding us. For now, we remain here, within the reality that has given us both consciousness and curiosity. We are small patterns of matter briefly able to notice the darkness, measure it, and wonder whether it contains another beginning. The question stays open, resting gently at the edge of knowledge, and beyond that edge, whether there is one universe or an endless hidden architecture of worlds. Nature continues in silence, needing neither our certainty nor our understanding to be complete.